Hello everyone, I'm TH, a certified flight instructor. Welcome to our virtual ground school explainer. Today we are going to take a really meticulous deep dive into the completely fascinating world of aircraft systems and structures. We're going to examine everything, and I mean everything, from the aerodynamic forces acting on an airframe all the way down to the specific chemical properties of the materials holding it all together. It's going to be a fantastic journey, so buckle up. Here is our flight plan for today's explainer. We'll start with number 1, aircraft systems and subcomponents. Then number 2, the evolution of aircraft structures. Number 3, we'll dive into the composite materials revolution, followed by number 4, composite hazards and protection. And finally, number 5, we'll step inside the flight deck and look at instrumentation. Let's get right into it. Section 1, aircraft systems and subcomponents. Starting right up at the nose of the airplane, we have the engine compartment, which is securely wrapped in the cowling, and of course it's driving the propeller. Now, a propeller isn't just some generic fan bolted to the front, it's actually a highly engineered airfoil in its own right. Propellers are usually matched to a very specific aircraft and power plant combination to achieve absolute maximum efficiency at a particular power setting. And depending on exactly how the engine is mounted, they'll either pull or push the aircraft through the sky. But to truly understand how they generate that thrust, we need to talk about two very critical terms. Those terms are pitch and angle of attack. Now, please do not gloss over these. They are absolutely crucial. Pitch is defined as the theoretical distance a propeller would travel in one solid revolution if it were turning in a solid medium. Think of it like a screw driving into wood. Angle of attack, or AOA, is entirely different. It is the continuously changing angle at which the relative wind meets the propeller blade. Because it's measured against the hub, the built-in twist of the propeller blade keeps this AOA relatively constant all along its span, which significantly reduces the possibility of a stall. Just remember, the amount of lift, or in this specific case, thrust, produced is directly related to that continuously changing AOA during your flight. Moving slightly beyond the propeller, the core subcomponents of any airplane are going to include the airframe, the electrical system, the flight controls, and the brakes. The electrical system is what generates and distributes power, typically using engine-driven alternating current, or AC, generators, auxiliary power units called APUs, and external power on the ground. All of this feeds vital systems like your anti-icing and avionics. But actually, I want to share a practical CFI tip right here regarding the brakes. In modern airplanes, hydraulic brakes work by squeezing caliper pads against a steel or carbon material rotor. Because they absorb absolutely enormous amounts of energy and heat to slow the wheels down via friction, their life is actually measured in landings, not miles. Section 2, evolution of aircraft structures. So, this brings us to a really fascinating evolution in structural engineering. Early aircraft used what's called truss construction. This was basically lengths of tubing, called longerons, welded into a well-braced square or rectangular framework. The main drawback? A total lack of any streamlined shape. Designers literally had to add extra formers and stringers just to shape the cloth fabric covering over it. As technology progressed, aviation moved to monocoque construction. This method uses stressed skin to support almost all the loads. And this brilliantly illustrates a common analogy. Think of an ordinary aluminum beverage can. It supports considerable force at the ends if you press down, but if you slightly deform the side while it's supporting a load, the whole thing collapses easily. Now, monocoque design is incredibly weight efficient because it completely eliminates all that heavy internal bracing, but early on it was notoriously complex to build. Case in point, here's a fantastic historical anecdote from 1918. Aviation pioneer Jack Northrop devised a totally new way to construct a monocoque fuselage for the Lockheed S-1 Racer. Instead of painstakingly gluing hundreds of tiny strips of wood, he took 3 large sets of spruce strips, soaked them in glue, and laid them inside a semicircular concrete mold. Then, under a tightly clamped lid, he inflated a rubber balloon right in the cavity to press the plywood perfectly against the mold. 24 hours later, he had a perfectly smooth, lightweight half shell. Brilliant, right? But because pure monocoque acts like that fragile aluminum can we talked about, modern aircraft predominantly use semi-monocoque construction. If you look closely at how these are built, you'll see a complex substructure attached directly to the inside of the airplane's skin. We have bulkheads, formers of various sizes, and longitudinal stringers. These reinforce that stressed skin by taking a significant portion of the bending stress, totally preventing that beverage can deformation. Also, right at the front of this structure, we have a vital safety feature, the firewall. Usually made of a heat-resistant material like stainless steel, it serves as a fireproof partition, literally protecting the cabin from accidental engine fires.
Section 3. The Composite Materials Revolution.
Composite is a pretty broad term, but it represents the incredible shift away from traditional metal and wood. Its integration into aviation has a rich chronological history. It actually dates all the way back to World War II, where soft fiberglass insulation was used in B-29 fuselages. Jumping to 1965, the FAA type certified a high-performance Swiss sailplane called the Diamond HBV, which famously utilized fiberglass for its primary structures. Just 4 years later, in 1969, the Windecker Eagle became the very first all-fiberglass aircraft certified in the normal category. Fast forward to 2005, and we see over 35% of new aircraft being constructed of composite materials.
So what exactly is a composite? At its core, composite materials are fiber-reinforced matrix systems. The matrix is essentially the glue, most commonly an epoxy resin, which is a thermosetting plastic that holds everything together and gives the part its physical shape. But the fibers are what actually carry the load. Let's compare the two main ones. Fiberglass has good impact resistance, is inexpensive and readily available, but it is somewhat heavy. On the other hand, we have carbon fiber. It is incredible stuff, often 30% lighter than an equivalent aluminum structure, with much higher bending stiffness. However, it is relatively poor in impact resistance. Those carbon fibers are brittle and tend to shatter under sharp impacts. The advantages of using these materials are just immense. First, composites allow for extremely smooth, compound-curved, highly aerodynamic structures that drastically reduce drag. This is exactly why sailplanes and modern aircraft like the Cirrus use them. Second is a complete lack of corrosion. Boeing designed the 787 with an all-composite fuselage, which allowed them to run both a higher pressure differential and higher humidity in the cabin than previous airliners. Why? Because the engineers simply no longer had to fear moisture condensation rotting the hidden fuselage skins. Third, composites offer far superior performance in a flexing environment. They do not suffer from metal fatigue and crack growth like metals do, which gives things like helicopter composite rotor blades and hubs considerably higher design lives.
Section 4. Composite hazards and protection. Now, let's shift our tone to a very serious, safety-focused CFI perspective. When an aluminum fuselage gets bumped, it dents. The damage is totally visible. Composites respond completely differently. With a low-energy impact, you get a pyramid pattern matrix crack. The surface might look completely fine to you, but underneath, extensive cone-shaped delaminations are silently spreading on the backside of the structure. The damage can be massive and structural, yet entirely hidden from your naked eye on a standard walk-around. Let's walk through the 3 distinct stages of impact severity. First, a low-energy impact, like accidentally dropping a wrench, leaves almost no visible sign on the surface, but damages the backside. A medium-energy impact, perhaps a tug or car bumping into a hangar door, results in local crushing of the surface that is visible and definitely requires repair. A high-energy impact, such as a bird strike or hitting hail in flight, results in a full puncture. Here is a vital tip for you. Anytime you are inspecting a fiberglass structure on a walk-around, always look for whitish areas. The appearance of a whitish area is a telltale tip-off that delamination of the fiber fracture has occurred underneath the resin.
Now, let's talk about another completely hidden hazard, heat. I want to drill this specific number home, 220 degrees Fahrenheit. While too hot technically depends on the specific resin used, many epoxies begin to critically weaken at just over 150 degrees Fahrenheit. If you have an aircraft with a composite wing painted black, and you park it facing a black asphalt ramp on a hot, sunny day, that structure can easily reach a dangerous 220 degrees. This is exactly why composite aircraft often have strict, specific recommendations for allowable paint colors, frequently requiring white paint to reflect that thermal energy. To put it in perspective, even a quickly extinguished small brake fire can permanently destroy a composite landing gear leg. We also have to actively protect composites from lightning and chemicals. You see, fiberglass is an electrical insulator, while carbon fiber conducts electricity very poorly. Therefore, lightning protection requires fine metal meshes, usually made of aluminum or copper, bonded directly into the outside layer of the composite skin. This safely conducts that massive electrical energy overboard and away from your delicate avionics. By the way, because fiberglass is transparent to radio frequencies, you'll very often find internal radio antennas placed strategically behind special windows cut into that lightning mesh. Lastly, chemical hazards. Never use chemical paint strippers on composites. They will literally ruin the matrix. And if an aircraft uses inexpensive polyester resins for its fuel tanks, ethanol-blended autogas can actually attack and dissolve the composite, though more expensive epoxy resins handle it just fine.
Section 5. Flight deck and instrumentation. Let's conclude our physical walk-around and step inside the flight deck to see how we actually command these complex structures. The contrast here is fantastic. You have traditional analog displays like in a classic Cessna 172, equipped with individual conventional mechanical instruments. Then you have the modern electronic flight display, commonly known as a glass cockpit. These utilize multiple liquid crystal display, or LCD screens. The screen directly in front of the pilot is called the primary flight display, or PFD. The second screen, usually right in the center of the panel, is the multi-function display, or MFD. These solid-state instruments brilliantly declutter the instrument panel while massively increasing safety, boasting a failure rate far, far less than those of conventional analog gauges.
Regardless of whether you are flying with old-school analog dials or a high-tech digital glass panel, every single instrument falls strictly into one of three categories: performance, control, and navigation. Performance instruments like your altimeter, airspeed indicator, and vertical speed indicator show the actual performance of the aircraft. Control instruments, most notably the attitude indicator, display immediate attitude and power changes. Note that carefully. The attitude indicator does not indicate altitude or speed, it only shows your immediate pitch and bank. You must cross-reference your performance instruments to see the results of those control changes. Finally, navigation instruments, which include things like your glide slope and course indicators, tell you your exact position relative to a ground facility or a GPS fix. Speaking of navigation, the most ubiquitous system we use today is the Global Positioning System, or GPS. It's a satellite-based navigation system originally intended exclusively for military applications by the United States Department of Defense. But it was made available for civilian use back in the 1980s. To actually figure out where you are anywhere in the world 24 hours a day, a GPS receiver must lock on to specific numbers of satellites. It explicitly requires a signal from at least 3 satellites to calculate a 2D position. That gives you your latitude and longitude. But to determine a 3D position, which adds your critical altitude data, the receiver requires 4 or more satellites in view.
We've covered a tremendous amount of ground today, from the aerodynamic perfection of pitch and angle of attack, through the fascinating evolution of stressed skin monocoques, into the high-tech, heat-sensitive world of composite resins, and finally settling in to the GPS-guided glass flight deck. So I want to leave you with this question. From welded steel tubes to all-composite, GPS-guided aircraft, what hidden details will you be looking for on your very next pre-flight walk-around? Remember to check for those whitish spots on your fiberglass. Thanks for joining this virtual ground school explainer. Keep learning, stay safe out there, and I'll see you next time.